what we are going to do in this frame is to explain how we can decide whether a circuit is stable or not in S domain rather than in time domain, because we are dealing with the analysis in S domain. We will be dealing with analysis in S domain, so we should be able to decide whether a circuit is stable or not without passing to time domain. So by examining this list, we can make that decision. How we are going to make it? We know that when we do the analysis at the end, we are going to end up with a rational function. A rational function is something like that. We end up with rational function means element currents and voltages after the calculation is going to be a rational function. Rational function is something like that. Sm plus B Am e to A minus 1. Oh, sorry, let's make it a polynomial I am trying to write here. There's going to be a rational function. That means denominator and numerator is going to be polynomials. This is a mth order polynomial. Goes end up with A0 and over here Sn plus Bm minus 1 Sm minus n minus 1, of course, goes and end up with B0. So this is a rational function. That's the polynomial denominator, numerator, and the denominator polynomial. Now this polynomial is characteristic equation. In time domain. So the root of this equation, so this, if you say this equation is equal to 0, we don't say this is a polynomial anymore, it becomes an equation. Roots of these equations are called characteristic roots. Now we are going to make the decision how we are going to say whether the circuit is stable or not by looking at the characteristic roots here. These characteristic roots are going to be in S-plane. So let me draw the S-plane here. So, oh sorry, I'm going to clear that area, make it a bit better. And this here. That is S-plane. What we are saying S-plane here, we can represent all the characteristic roots on that plane if this is the real part of it, which is alpha, and this is J beta here. Any complex number can be shown here. Any real number also can be shown here, isn't it? Real numbers is going to be on this axis, and imaginary numbers are going to be on this axis. Any complex number is going to be on this plane. So we are saying we can represent all the characteristic roots of this equation on this plane now. So according to characteristic roots position on that plane, we can say that whether the circuit is stable or not. How we are going to say it, I will be explaining here. So there are three types of roots that we are going to see: real roots, complex roots, repeated roots or multiple roots, or multiple complex roots or repeated complex roots. Repeated, sometimes it might be called multiple as well. Now, if now What these are the characteristic roots. When you write this function, that rational function, as the summation of the fractional fractions, each fraction represent one of the roots. So these roots could be, fraction roots are going to be something like that. Fractions related, each root is going to be any of those. So I will be examining any of those separately. Saying that, if the characteristic root, let me write it here, characteristic root, positive, or I mean, let me say negative first. Characteristic root is negative means, in here isn't it, negative real. It's going to be somewhere here. This is alpha value, isn't it? Alpha value. If j value is 0, so any complex number is going to be j beta here. So if you say that b is 0 and alpha is negative, that is characteristic root is real and negative. So you are on this line now. So we are saying at this moment, that means that's going to be minus a, that's negative, exponentially decreasing function. Exponentially decreasing function, when t goes to infinity, it becomes 0. So it is stable. So if it is, characteristic root is positive real, then this is going to be positive, isn't it? If it is positive, it becomes e to the power t. That means exponentially increasing function. When t goes infinity, this function goes to infinity. So that means astable, isn't it? It is astable. When the characteristic root is positive real, that means you are in here. So if it is repeated rule, real, negative real, repeated, negative, maybe I write it out, negative, repeated, real. So that means that was repeated. So if this one repeated, I am talking about this, isn't it? This is single, that's repeated one. So my t domain function is going to be like that. If it is negative, that's going to be exponentially decreasing. If you apply the t over e to the power alpha t, when t goes infinity, this goes infinity, this goes infinity. So that is undetermined. So if you apply the Hospital rule, so that's going to be 1 over alpha times e to the power alpha t. When t goes infinity, this goes to 0. So that disappears. So no problem, it is stable, isn't it? So if the characteristic root is real and repeated, so in this case, when it is real negative, it's going to be in here. So we can show that repeated. So if I put it in a circle, that shows that repeated, let's say. So it is stable. So let's consider the same thing for the positive. So that means positive, repeated, real. So we are going to be in here. When it is positive real, it's going to be in here. So this time, this is going to be now positive. So t to the power t, when t goes infinity, this goes infinity. So therefore it is stable. Unstable. Unstable, unstable, same thing. Isn't it? Because this doesn't go underneath anymore. So it's going to be t times e to the power alpha t. So when t goes infinity, this goes infinity, since this is positive. So this is generalization, so we leave it. So if we come to the complex now, so the complex number, if the real part of the complex root real part is negative. What happens? So complex root real part is negative, is going to be somewhere here, isn't it? So real part is negative. Because of that alpha is going to be negative. J beta could be this one, isn't it? We know that if there is a complex root like this, the complex conjugate of this root, which is symmetrical according to that axis, is also a characteristic root. We know that. So in this case, our t-domain function is going to be like that. Since this is negative here, and this is changing between plus and minus, since this is cosine function, so this is exponentially decreasing function, so it's going to be stable. But if the complex root real part is positive, real part is positive, so that means we are here somewhere. So the alpha is going to be positive for this complex number, and complex conjugate of this complex number will also be the another characteristic root. So if we are in this area, then it's going to be unstable, because this is going to be this time e to the power alpha t. So when t increases, this is increasing. This term is going to be a value between plus minus 1. So this goes to infinity when t goes to infinity. So because of that, it is unstable. What happens if these complex roots are repeated, or multiple roots? So if it is multiple, let me show it like this here. If it is multiple, yeah, it is something like that. It's going to be multiple, isn't it? So when it is multiple, it becomes t, but since it is real part is negative, so this is going to be, when you apply the Hospital rule, this is going to go to a real number. It doesn't go to infinity. That's why it is real part is negative, real part negative, and repeated, then it is stable, isn't it? I should have written in the black this one. Let me make it black, then I can do it. So if it is negative, it's going to be e to the power minus at. So if you apply the Hospital rule, this is going to be a definite number. So if it is real part is positive repeated, then it becomes unstable. So that's this case, isn't it? Here that is stable. Multiple case, I put it in a circle here. It's going to be stable. Why is that? Because this is positive, means that is exponentially increasing. This is increasing as well, multiplying of two increasing functions. That means your function goes to infinity when t goes to infinity. So the last thing left is what happens on this line. That means if the characteristic root is imaginary roots. So if it is on this, if it is on this, means alpha is equal to 0. If alpha equals to 0, so alpha is 0, that means you are on this line. I put 2 here because if there is an imaginary root here, the complex conjugate of it, this should also be a characteristic root. So in this case, this term is going to be 0 when there's no multiple case. This term is 0. This becomes a value between plus minus 1. So it's going to be a definite number. Then it is stable. Non-repeated case, imaginary root. So if it is alpha is equal to 0, repeated one, it is going to change now. Alpha equal to 0, repeated, or multiple root, multiple imaginary. So that means this type, isn't it? This circle shows it is multiple or repeated. So let's examine now. When it is repeated, that t comes in. So this is going to be 0. So I'm talking about this now. This term is going to be 0 when it is repeated. So this is going to be in between plus minus 1. So t here, because of it is repeated. If it is non-repeated, there is no t here and it is stable. If it is repeated, this is going to be 0. This is going to be 1. I made a mistake. This is not 0. This is 1. Let me correct it. This is in between plus minus 1. So the t is the multiplication of this. When t goes infinity, this goes infinity, so it is unstable here. So that's why I put it in red here. So after having said all that, the conclusion, we can explain the conclusion in simple words. How we are going to explain it? We are going to say that if the characteristic roots are on the left hand side of S-plane, that is this sign, left hand side of the S-plane, or and non-repeated imaginary roots, so that means we are including this, non-repeated. So let me write non-repeated here. Non-repeat left hand side and or non-repeated imaginary roots we have, then circuit is stable here. If the characteristic roots are on the right hand side of the S-plane, that's this part, isn't it? Or characteristic roots are imaginary roots and they are repeated. So these are repeated. Then circuit is stable, isn't it? Let me say the same thing in different ways. One of them, if you are left hand side of S-plane, it is stable. If you are right hand side of the S-plane, it is unstable. If you are in J omega axis, so J beta axis, that means imaginary roots. If it is non-repeated, it is stable. If it is repeated, it is unstable. That is the conclusion and also the end of this frame.